Of all the different classes of compounds that exist, there are two, acids and bases, that are fundamental to the functioning of our world. They are essential for life. They are at the heart of a host of processes in nature, and they are important in many industrial products and processes. We are going to examine the properties of acids and bases and illustrate how these compounds influence our world. Acids. The very word evokes the image of dreadful burns and corrosive liquids that eat away at almost everything. And yet, there are many different types of acids. Some, like ascorbic acid, better known as vitamin C, are essential for life. When they are dissolved in water, acids make solutions that taste sour or tart. Foods that contain acids include citrus fruits, cheese, vinegar, and sour milk. Soda pop is also a mild acid. Bases have a bitter taste. Soap and cleaning materials are bases, and anyone who has accidentally put soap in his mouth can attest to the bitter taste. To the touch, acids feel like water, but eat an orange when you have a sore in your mouth, and you will find out that even mild acids can sting. Bases, on the other hand, feel slippery, like soapy water. Both acids and bases are electrolytes, good conductors of electric current. Acids react vigorously with metals, such as zinc, iron, aluminum, and magnesium. This is a piece of magnesium in hydrochloric acid. The reaction produces hydrogen gas. Bases, on the other hand, do not react with metals. Chemists can use these and other tests to determine if solutions are acids or bases. But a much easier and more accurate test is with pH indicator paper. This special paper reacts with both acids and bases. A base turns indicator paper blue, and an acid turns it red. Chemists use indicator paper as a quick and inexpensive test of solutions. The 17th century English chemist Robert Boyle was the first to study acids and bases in a systematic way. Boyle found that these two types of compounds counteract each other. Acids react with bases so that the properties of both are lost to form water and a salt. This process is called neutralization. Boyle's observations were an important advance, but he could not explain why these reactions were happening. It was not until the late 19th century that a Swedish chemist, Svante Arrhenius, made the first steps to unravel this mystery. Arrhenius found that water often could dissolve both acids and bases by separating them into individual ions. For example, hydrochloric acid, HCl, separates in water. What has happened in this reaction is that the original molecule, made up of one atom of hydrogen and one atom of chlorine, dissociates in water into its constituent H+ and Cl- ions. The hydrogen has become a positively charged ion, or cation, while the chlorine has become a negatively charged ion, or anion. Hydrogen has only one proton and one electron, so a positive hydrogen ion is one simple proton. Arrhenius found a similar process works when bases are dissolved in water, but rather than releasing a positive hydrogen ion, it generates hydroxide ions, OH-. For example, when sodium hydroxide, NaOH, is dissolved in water, this is the reaction. In water, the sodium hydroxide dissociates. The sodium, Na, becomes a positive ion because its electron has gone to hydroxide, OH-, which is a negative ion. Arrhenius summarized his findings by defining acids as substances that release hydrogen ions, H+, when dissolved in water, and bases are substances that generate hydroxide ions, OH- when dissolved in water. This definition explained a number of things. It showed that acids have similar properties and bases have similar properties. It solved the mystery as to why acids and bases neutralize each other. When these two substances are mixed together, the H+ from the acid mixes with the OH- from the base to produce H2O, water. Arrhenius was also able to show that in the neutralization process, when an acid and a base are combined, they produce water and a salt. The general equation is acid plus base produces water plus salt. For example, when hydrochloric acid is combined with sodium hydroxide, a base, it produces water and an ionic compound called a salt. We think of salt as table salt that we put on food, but there are many different salts, all of them ionic compounds. Arrhenius's explanation of acids and bases was an important advance, but there were problems with it. His definitions could not explain why a number of products, like baking soda, acted like a base but did not have any hydroxide ions. His explanation also is limited to the reactions of acids and bases in water. In 1923, a Danish chemist, Johann Brøndstad, and an English chemist, Thomas Lowry, published independent but similar findings that refined Arrhenius's work. Their theories have come to be called the Brøndstad and Lowry definition of acids and bases. The definition that they used for acids was similar to Arrhenius. An acid, they said, was any substance that can donate a hydrogen ion, or proton. But their definition of a base is very different. They define a base as any substance that can accept a proton. Essentially, a base is the opposite of an acid. The Brøndstad-Lowry definition expands the number of substances that can be acids and bases and shows the close relationship between them. It explains why substances that do not contain OH- can act like bases. Under the Brøndstad-Lowry definition, both acids and bases are related to the concentration of hydrogen ions, or protons, present. Acids increase the concentration by donating protons, while bases decrease the concentration by accepting them. Therefore, the acidity or basicity of something can be measured by its proton concentration. Some acids, like vinegar, are relatively mild. If you spill a little on your hand when you put it on a salad, there is not much to worry about. But others, like hydrochloric acid, HCl, are very strong and can be extremely dangerous. As the two solutions sit in beakers, they look virtually the same. But why is one so much stronger than the other? A strong acid is one that readily transfers H+ ions to water. The more complete the transfer of hydrogen ions, the stronger the acid. For example, when hydrochloric acid is mixed with water, nearly all of the HCl molecules transfer the H+ ions to water to yield ions of H3O+. By contrast, a weak acid, like vinegar, does not dissociate or transfer H+ ions as readily in water. Only 0.4% of the acid molecules in vinegar transfer their H+ ions. That 99.6% does not dissociate. That is why vinegar is such a weak acid and why hydrochloric acid is so strong.